Warning, all attendees are in listen-only mode.
Good morning. I'm Neil Polhemus. Today's webinar is titled Introducing Statgraphics 18. We're going to take a look at the new features added to the latest version of Statgraphics, and I'll be giving you a general overview of what it contains. As with all of our webinars, you're encouraged to submit questions through the GoToWebinar facility that you're using. We will hopefully talk for about 45 minutes, and after that I'll take a look at whatever questions have been submitted and try to answer those as best I can. Statgraphics 18 is the 18th version of Statgraphics for PCs. The very first version was released about 35 years ago now, in 1983, obviously back in those days running under DOS, not under Windows. But the current version, which we released last year, is the 18th version of the product. The newest version, Statgraphics 18, features 30 new statistical procedures, brand new procedures added to the Statgraphics menus. It also includes significant enhancements to 18 existing procedures. There are new file formats and improved methods for handling big data. And when I talk about big data, I'll be referring to data files with millions of rows and hundreds of columns. And I'll show you an example of that as we go through here today. There are expanded dialogue-based interfaces to some of the more useful procedures in R. We've streamlined the activation process to hopefully make it easier to get up and running once you have a serial number. And we've also added a concurrent user network license manager that allows users to check out seats for temporary use on their own laptops. Today's webinar is as follows. I'll start by talking about the general interface, what we've done to the interface. I'll show you methods for handling big data with a particular example that contains about 7 million rows. I'll show you some of the newer procedures for visualizing data, and then talk about one of the important additions to the statistical capabilities of the program, and that is the addition of equivalence and non-inferiority tests. I'll talk about some new process capability analysis features that we've added that support the latest book that I wrote on that particular topic. We'll talk about enhancements to the R interface, and we'll talk about changes to the installation program. Now, I'd like to emphasize that today's webinar is going to be an overview. It's not going to dig deeply into any one of those procedures. However, there are 50 videos that are available online, and you can see the link at the bottom of that screen, that do show you in detail the features that have been added to version 18. So if you're interested in a particular topic, you can get a lot more information by digging into those particular videos. When you load up Statgraphics 18, if you've used Statgraphics before, you'll notice that the interface has not changed a lot. In fact, you'll see only two differences. First off, you'll see a new menu item labeled R Interface. This is where you go to access the dialog box procedures that call some of the more useful features of R. R contains a lot of packages that can do some interesting types of statistical analysis. And what the R interface does is make it easy for you to take data directly from the Statgraphics data sheet, select various options with R dialog box, and then have R execute those procedures and we'll grab the output from R and put it back into Statgraphics. That particular menu item shows you the packages in R that we've currently linked to. The second major change is in the data sheet. You'll see that there's a third row in the header now that indicates at any particular point in time the type of each column. If you're familiar with Statgraphics, you know that every column in Statgraphics has a type. Before you had to click on the name of a column to see what type it was. Now there's a third row that automatically shows you what's there. Now, talking about columns and the fact that every column has a type, Statgraphics 18 added two new types. The first new type of column is what's called a censored numeric column. It's a column in which you have numeric data, some of which, however, may be censored, either left censored, right censored, or interval censored. And you can enter directly into the cells of the data sheet expressions like less than 0.1, greater than 100, and a bracket from 10 to 20 if you have interval censored data that might be anywhere between 10 and 20. Now, this particular data type was constructed because of the interface to the R procedure for fitting distributions to censored data. You can simply pass a column like that to the distribution fitting procedure, and it will fit any of a rather large number of distributions. The second new data type is a currency data type, where you can enter monetary values, and you'll have the choice of a dollar sign, a euro symbol, a British pound symbol, or a symbol for Japanese yen. Those symbols appear in the data sheet. They also appear on output, including graphs, similar to what we've done for things like dates and times and percentages, but now we've also done it for currency. As I said, there's a new menu item giving access to R. You'll see on the R interface menu that there's a choice menu item for installing and configuring R. The menu items exchange data and execute script. They were there in version 17. But the other 5 menu items, starting with classification and regression trees, show you the new interfaces we've built to some very useful packages in R. Classification and regression trees, distribution fitting, multidimensional scaling, text mining, and X13 ARIMA seats seasonal adjustment procedure. So currently there are 5 R packages that we've built dialog boxes to interface to. We're continuing to add additional ones, and you'll see some additions to that R menu very shortly. Now, when it comes to big data files, one of the things that Statgraphics 18 did was add a new data type. You're probably familiar with SGD files, .sgd. Those are standard Statgraphics data files. We've now, though, introduced a new file type, a .sgb. Statgraphics Big is what it stands for handling very large amounts of data. The primary difference between the smaller Statgraphics data files, SGD files, and the big data files is that the big data files hold numeric data in binary format rather than as text. Standard Statgraphics data files are XML type files that you could actually edit in any text editor. Big data files, Statgraphics big data files, hold the data in binary format. Now, the advantage of that is that when you read data into memory, you don't constantly have to change it from text to numbers. So it's much faster to take millions of observations and pull them into memory when you don't constantly have to change them from text to numbers. Another big change or big difference between ordinary Statgraphics data files and big data files is that the files are organized by column rather than by row. And by that we mean that if you looked at the way the data is held in those files, all the data for column 1 comes first, and that's followed by all the data for column 2, all the data for column 3, and so forth. It makes it much quicker to pull data for one or a small number of columns, which you're frequently doing in the Statgraphics procedures. If you had to read millions and millions of records from an ordinary Statgraphics data file where the data are arranged by row rather than column, it would take much longer to read the data from the file. Okay. How do you get and create big data files? Well, Statgraphics big data files are typically created by querying a database, downloading data into a text file, and then we have procedures to convert the text file to an SGB file. Obviously, when there are millions and millions of records, you're not likely to be typing all that information in by hand. Rather, it's being pulled from some other data source. And the way we suggest you do it is to create a text file, which then we will convert over to a Statgraphics big data file. Now, as an example of analyzing big data, I've pulled together information on all commercial flights in the United States in the year 2008. There are almost 7 million commercial flights in this particular database, and we know information about departure times, arrival times, departure delays, arrival delays, all those sorts of things. And what I'd like to do is actually now go into Statgraphics and show you how we can handle that type of big data. So I've loaded up Statgraphics 18, and I'll go now to File, Recent Data Files, and here I have a big data file. It's called 2008 Flight Data. Okay. You can see it takes only a moment to open up an interface to the flight data file. And if I were to take the my cursor here and scroll down to the bottom, you'll see that there's something in excess of 7 million observations in that particular data file. Okay, well, let's go ahead and do a quick analysis of that. Let's go to the Relate menu, One Factor Simple Regression. Now, as far as the procedures are concerned, the analysis runs the same on the big data files as it would an ordinary data file. So I'll pick a column, perhaps the arrival delays, as the dependent variable and the departure delays as the independent variable to see how the arrival delay of a particular flight depended on its departure delay. We can fit any of 27 different models to the data. You have all the regular options, and I'll just push the OK button, and now it's done the simple regression. You can see up in this analysis summary here that there were about 6,855,000 rows in that particular data file with complete data on both the arrival delays and the departure delays. The output is the same as you would normally see, with the exception of the plots. When we have big data plots and we want to do something like a plot of the fitted model, rather than trying to draw 7 million points on the plot, which would not be very informative, the program will automatically switch over to what are called hexagon plots. Hexagon plots take the X, Y coordinate system and divide it up into what's called a tessellation of hexagons. That is a set of non-overlapping adjacent hexagons, hexagonal regions at least, that fill that particular space. If there's no more than one or two observations in any particular hexagonal region, they'll be shown as individual point symbols. But if there are, by default, 3 or more points in any hexagonal region, it'll draw a hexagon, and the intensity of the color of a particular hexagon will indicate how many observations are in that particular region. That way, what would otherwise be just a big black blob is an informative plot. You can see that the highest density of observations is down here near the origin and very close to the regression line, which you see the equation at the top of the screen. Now that's useful in looking at the plot of the fitted model. The same thing will also be useful, for example, if we look at the residual plots, and the program automatically switches. Now, if I go to edit preferences, you'll see that there is a new Big Data tab. And the Big Data tab has settings that control when the hexagons are shown rather than ordinary scatter plots. I have it set so that hexagons will be shown if there are 100,000 or more observations. Okay? It also won't plot scatter plots if the panes are minimized, the graphs are minimized, if there are lots and lots of observations. As far as the hexagons themselves are concerned, I've taken the defaults, which is to have 50 hexagons along both the X and Y axes. It'll show a hexagon as soon as it sees 3 or more observations in a particular region. And the minimum color intensity I have set here to 50. You can change those to get different effects. Now, one other comment about big data while I'm talking about big data, and that has to do with judging statistical significance. Once you start working with millions and millions of observations, you'll see fairly quickly that all your p-values will end up being 0. I mean, with almost 7 million observations, even rounding error tends to look significant. So we begin at that point to forget about whether things are statistically significant or not and start worrying a lot more about whether they are practically significant. Okay, does a slope of, for example, 1.01865 mean anything? Well, that would be a judgment call, obviously, that a subject matter would have to make. Correlation coefficients, they're still useful. R squared, they're still useful. Really, everything on the screen is useful except for the p-values. Okay. Well, that's a typical example of analyzing a big data file. Now let's talk about some other things. One of the other additions to Statgraphics version 18 were new procedures for visualizing data. Obviously, I've always been interested from the very first version of Statgraphics in doing visualization. And we've added a few new procedures, one of which is called a Violin plot. Now, Violin plot's a very nice plot for visually displaying data. And in this case, the data I'm going to be looking at is 272 measurements of the duration of the eruption of the Old Faithful geyser in Yellowstone National Park. Okay, the duration of eruptions typically ranges from about 1.5 minutes to 5 minutes. And you can see that in a Violin plot, you actually start with an ordinary box and whisker plot. Now, an ordinary box and whisker plot is a great method for summarizing the distribution of a set of data, a quick summary. What it doesn't show, though, is one important aspect of the eruptions of the Old Faithful geyser, and that is that it's a very bimodal distribution. You wouldn't know that from the box and whisker plot itself, but in fact it's true. In a Violin plot, what you do is you start with that box and whisker plot and then add a non-parametric estimate of the density function to the plot above and below the box and whisker plot. So what you see here, if you look at the upper curve, is an estimate of the probability density function of the duration of the earthquakes. And you can see the strong bimodal nature of the eruption duration. There's one peak here at about 2 minutes, another peak up at around 4¼ minutes. A very strongly bimodal distribution. You don't get many eruptions of Old Faithful that last only 3 minutes. They're either 2 minutes or they're a little over 4 minutes. So a very nice, I think, way of adding information to a box and whisker plot. We've also added to a box and whisker plot something called a diamond plot. The diamond plot shows you the width of a 95% confidence interval for the mean. If you recall how the box and whisker plots are structured, there's a vertical line at the median and typically a plus sign at the mean. Well, the distance covered by this diamond shows me how well I've been able to estimate a population mean by showing me a confidence interval. It's a nice addition, I think, to a box and whisker plot. We've also added several dynamic statlets. We've added a population pyramid, we've added a windrows, and we've added a demographic map. Now I'd like, if I can, to actually show you those because these are dynamic procedures. So I'm going to open up Statgraphics 18 and I have stored away a Statfolio that creates a population pyramid. Now if you're not familiar with a population pyramid, what a population pyramid does is it divides members of a population up into different age ranges. For example, I'm going to show you here a bar or a class, at least, for children aged 0 to 4, people aged 5 to 9, 10 to 14, all the way up to a category for people 85 or more. You have the number of males in millions shown with the blue regions and the number of females shown by the red. Now this slider here will change the year, and this is what makes the plot so interesting. I'm going to move it all the way back to 1950. What you'll see in 1950 is that there are many children aged 0 to 4. That's what we refer to in this country as the baby boom. Right after World War II, all the GIs came back, started to have families. So you had lots and lots of babies born right after the war. I can push this button here and now have the year change interactively. And you can pretty much follow the baby boomers as they get older and older and older. You can also see that by 2012, there were many more individuals in the population that were 85 and older, in particular females. By 2012, there were about 4 million females in the U.S. 85 years or older. That's a pretty neat application of what I call dynamic data visualization. Another one that's interesting is something called a windrows. A windrows is used to display the distribution of wind direction and wind speed at a particular location. What we've done here is taken data over several months and at a particular time of day, in this case midnight, show by the size of the petals how frequently the wind was coming from a particular direction. So at this particular location at midnight, the wind was predominantly coming from the south-southwest. The color of the bars represents the wind speed. And you can see at midnight it was common to have winds between about 5 and 10 miles per hour. Now what's interesting here, this is also a dynamic statlet. I can let time of day change, and you'll now watch it cycle through the hours. And if I go back to around, that's around 2 o'clock in the afternoon, you'll see that the wind has shifted more toward the west than to the south. And you'll also see that occasionally you'll have the wind coming from the northeast. So it's a very interesting way to watch the winds change. Very useful if you're setting out runways at an airport or a field of wind turbines or something like that. One additional statlet that was also added to version 18 was a demographic map. A demographic map where we showed the value of some variable at different locations. Now what this map is going to show you is the size of the major cities in the United States beginning in 1790. Okay, the size of the bubbles here will represent the population, and you can see in 1790 the major cities in the United States were all along the northeast coast from Virginia up into Massachusetts. Now if I let the year vary, and it'll jump and show you the how things change from one census to the next, you can watch the growth of the cities. Notice that the westward expansion really began back here in about 1850. And that's the first time you saw any population out in California. And from then on, spread throughout the rest of the country. There's a lot you can do to add information to statistical graphics if you do some animation as I did here. Okay. Well, let me go back to my slides again for a moment, because I want to talk about some of the statistical capabilities that were added to Statgraphics. One of the major areas where we added some statistical capability was in running what are called equivalence and non-inferiority tests. These tests are designed to demonstrate that two population means are equivalent. That would be an equivalence test, or that one mean is not inferior to the other. That would be a non-inferiority test. This test might be run, for example, if you're a pharmaceutical company, you're creating a generic drug, and you might like to demonstrate that the generic is equivalent to the brand name drug. Now, equivalence and non-inferiority tests differ from standard two-sample hypothesis tests, because two-sample hypothesis tests, the normal tests you're used to, t-tests and that sort of thing, are designed to demonstrate that two means are different, not to demonstrate that two means are equivalent. You can also, using the Statgraphics procedures, compare one mean against a target value to show that the mean of a particular sample is not significantly different from a target. Now, the way this is done, technically, is as follows. Let's suppose I have two means, the mean of a generic drug and the mean of a brand name drug. In an equivalence test, I would like to prove, and the thing that I want to prove always goes in the alternative hypothesis, I'd like to be able to demonstrate, beyond a reasonable doubt at least, that the difference between the means is greater or equal to some lower equivalence limit and less than or equal to some upper equivalence limit. I might like to demonstrate, for example, that the difference between the means varied between minus 10% and plus 10%. Okay? As a null hypothesis, we have the following. If this is the alternative that I'd like to demonstrate. The null hypothesis would be that the difference is less than some lower equivalence limit or greater than some upper equivalence limit. So there are actually two parts to the null hypothesis. The null hypothesis says that the difference is either less than some lower value, which would be negative, or greater than some upper value, which would be positive. We'd like to be able to reject that null hypothesis in favor of the alternative, and if we can, then we'll say we have demonstrated equivalence between the means. The inferiority test is similar, except you have only a single limit. So you'd like to show, for example, that the difference between the means is no less than minus 10% or something like that. Okay. Now, I'm going to show you in Statgraphics how we do this. Put this away for a moment, get back to the program, and I'm going to load up a data file which is called equivalence. I know I have that here. Here it is. What this particular data file has is 25 measurements using method A, 25 measurements using method B, and 25 measurements using method C. My goal is to demonstrate that method A is equivalent to method B and equivalent to method C. You'll find that on the Statgraphics menu now. If you go to Compare, Equivalence and Non-Inferiority Tests. There are equivalence and non-inferiority tests for comparing two samples, for comparing paired samples, for comparing a single sample to a target, and also for something called a 2x2 crossover study. Okay. I'm going to select the comparison of two independent samples because it can actually handle more than two, but it'll take them two at a time. I have a couple options for how the data are structured as I do same options as in multiple sample comparison. Here I'm going to tell it I have multiple data columns, and the data columns are A, B, and C. Okay. Now, when it comes to the analysis options screen, I choose here whether to run an equivalence test, that's a two-sided test, or to do an inferiority test to show that one mean is not less than another, or inferiority test where I want to show it's not greater than another. I have several options for how to handle the standard error. And again, you can look at the detailed videos we have on this for an explanation of all of those things. I do, though, have to define here what I mean by equivalent. By this, by entering minus 25 and 25 as our equivalence limits, we will define these means as being equivalent if the absolute value of the difference, you see, is no more than 25. When I press OK, it'll pop up a typical analysis window. You'll see the statistical results on the left. You'll see the graphical results on the right. Now, the method being used to show equivalence is something that we call TOAST, T-O-S-T, two one-sided tests. It'll run a t-test against the lower equivalence limit and a t-test with respect to the upper equivalence limit. For each of those one-sided tests, you get a p-value. So there'll be a p-value from testing against the lower equivalence limit, a p-value for testing against the upper equivalence limit. The greater of those p-values is the overall p-value for the test. And if it's less than 0.05, less than 5%, then you have demonstrated equivalence between the means. And you can see here that we have demonstrated that method A is equivalent to method B, but A is not equivalent to C. At least we haven't demonstrated that it is, nor B to C. You can also see that graphically over here where we show you the confidence intervals, in this case 95% confidence intervals for the differences between the means. Equivalent to the two one-sided tests is to simply look at the confidence interval. If it's entirely between the lower equivalence limit and the upper equivalence limit, then those two means are equivalent. We've demonstrated equivalence. And you can see that only A and B have a confidence interval completely between those limits. Okay, that was one of the important statistical additions to version 18. Now, I think I mentioned at the beginning of the webinar that last year I published a book titled Process Capability Analysis, Estimating Quality. It's published by CRC Press, and it covers various methods for estimating process capability. Now, one of the things I needed to do with version 18 is to be sure that we had in version 18 statistical methods that would implement everything in that book. That required adding a few additional procedures. The first thing we added to cover the contents of the book was an attribute capability analysis statlet. That's a statlet that estimates the capability based upon attribute data, and that included some Bayesian methods. We also added to the variables capability analysis statlet the ability to estimate Johnson curves. Johnson curves are curves that can match the mean, standard deviation, skewness, and kurtosis of a set of measurement data. We added a multivariate capability analysis for a situation where you had specifications on correlated variables. We added a procedure to estimate multivariate statistical tolerance regions, added control charts for capability indices, and also added a new procedure for estimating the required sample sizes, determining the required sample sizes for estimating capability indices. Now, I'd like to go back to the program and for just a moment show you these new procedures, at least a couple of them. First off, I'm going to go to the Statlets menu to Statistical Modeling Process Capability Analysis and pull up the Statlet for estimating attribute capability analysis. Now, this procedure can make use of either count data or proportions. Here it's set to estimate the proportion of non-conforming items. That's typically based on a binomial distribution, although it can also handle Poisson data. Now, taking a classical approach, I'll suppose that I took a sample of 800 items from some production process and saw one non-conforming item. What it will do here, using a classical approach, is estimate the proportion of non-conforming items using maximum likelihood. Actually, you see here on the graph not only the best estimate of the proportion of non-conforming items, but also a 95% upper confidence bound. Okay. And it shows you, in addition to those estimates, that's the proportion of non-conforming items, the best estimate, that's the upper bound. It'll also give you statistics for defects per million, yield, a z-score, a CPK, a sigma quality limit at both the estimates and the upper limit. So you can see that our CPK here is about 1.01 at our best estimate, only about 0.84, however, at our upper limit. Now that's the classical approach. If I switch to a Bayesian approach, okay, I can then start and define what's called a prior distribution for my degree of belief. in a Bayesian approach, you start with a prior for the parameter you're trying to estimate and combine the prior with the data. Now, we've given you a button here to help set the prior. And the easiest way to define a prior distribution is typically to pick 2 percentiles. I'm going to tell it, for example, that I'm 50% certain before I ever collect the data that the proportion of non-conforming items is no more than 0.5%. I'm 90% certain that it's no more than 1%. If I now press OK, it will create what's called a beta prior distribution. Combine that with the with the data, the likelihood function of the data, and come up with a posterior density function. Okay, the mean of the posterior density function is the Bayes estimator for the proportion of non-conforming items. We also use the 95th percentile of the posterior distribution as our upper bound. So we can do both classic and Bayesian estimation. As I said, we also added capabilities to the process capability analysis for variable data. Here's a data file containing measurements on the resistivity of 100 components. If I go to Statlet's statistical modeling process capability, this time go to variables, I'm going to give it my data on resistivity and tell it I have an upper spec limit of 500. What the Statlet will do is it will fit by default the normal distribution to the data, and based upon that normal distribution, give me estimates of CPK, PPK, defects per million, and so forth. Now, it'll also at the same time show me the results of a Shapiro-Wilk test for normality. That's a test of whether the data come from a normal distribution. A p-value of 0.0000 clearly implies that the normal distribution is not adequate. Well, here's the change. That was there in version 17. The new addition to version 18 is the ability to select a Johnson curve instead of a normal distribution. The Johnson curves are a set of distributions that can match any combination of skewness and kurtosis in the data. So what the program has automatically done here is gone through, tried various Johnson curves, and picked the curve that best matched the shape of the data. And then you can see modifications of the CPKs, the PPKs, the DPMs, and so forth based upon that fitted Johnson distribution. That was also new in version 18. Okay, a couple of the other things that we added to version 18, we added the attribute and variable capability analysis. We also added a multivariate capability analysis. This is a situation where you could specify limits on 2 or more variables. In this case, I've set specification limits on the diameter and strength of a particular product. It shows you the specification limits and draws an ellipse containing 99.73% of my estimated distribution. It's a bivariate normal distribution in this case, the ellipse being the equivalent of the 3 sigma limits that you'd have with only a single variable. We also have something called MCPK, that's a multivariate CPK statistic, which we can compute when we have 2 or more variables. There's a procedure in version 18 for calculating multivariate tolerance regions. Those are regions that will contain a specified proportion of a bivariate or multivariate normal distribution with a given level of confidence. There are actually two approaches that we take to that. We either do a Bonferroni approach, or we estimate the exact tolerance region, which is an elliptical region. So what you see here is actually two different types of multivariate tolerance regions. The ellipse is the exact one. I am 95% confident that at least 99% of all the items in the population from which we've taken this particular data fall within that elliptical region. Another thing we've added in the SPC section are capability charts, control charts actually, for capability indices. There is a control chart for CPK. Now, when would you use a control chart for CPK? Well, it's not uncommon for companies to take samples every day and compute CPKs every day. This would be a control chart that you would use to monitor daily CPKs where you had a target, for example, of 1.5. If you had a target CPK of 1.5, typically as long as it remained in the green or yellow regions, you'd figure that what you were seeing, even though your estimate might be low one particular day, was just normal sampling variability. The red region are the unusual values, unusually small values, unusual with some pre-stated probability, where we'd like to get an alarm. So this particular procedure, the capability control charts, are for people who routinely compute CPKs and want to monitor them against a particular standard. Okay. Well, those are some of the SPC changes. One of the other major changes we made for version 18 is the interface to R. R is a statistical analysis system that you can download for free and install on your computer. The problem is it's not a point-and-click type interface, it's a language interface. And if you're a statistician who spends all his time doing statistics, it provides a very powerful environment to do statistical analysis. On the other hand, if you're someone that can't devote full time to learning a language and would rather go through dialog boxes, what we've tried to do is build some dialog boxes that make it easy for you to access certain procedures in R directly from Statgraphics. And as I mentioned at the beginning, we've built interfaces to the X13 ARIMA seats seasonal adjustment procedure. That's the one used by the Census Bureau, to a procedure for non-parametric analysis of data which is arbitrarily censored, for text mining, which creates word clouds, for multidimensional scaling, and also for creating classification and regression trees. I wanted to show you quickly how the interface to R works, so I decided to show it to you using a very well-known data set. It's a data set having to do with irises, samples of different irises. There's something like 75 iris in this particular data set. We've measured each iris several things. We've measured the sepal length, the sepal width, the petal length, the petal width. And the irises, if you look through the file, are separated into three species. There's the species setosa, the species virginica, and the species versicolor. What a classification and regression tree will do is it will build a model that uses the first 4 columns to predict the 5th. It would be useful for classifying data. All right, let's go back to Statgraphics for a moment. Let's clear off what we were doing here and call up our iris data. It's one of my recent data files down here. There it is, iris. And you can see in the sample data file, well, actually, there's more. There's 150 iris, I forgot, of various species. Now, what we want to do is we want to use the tree program in R to analyze this data. And to do that, I'll go to R interface, classification and regression trees. Well, it's going to look very much like a Statgraphics procedure. I'll put in species as a dependent variable, the first 4 columns as quantitative factors. When we get to the screen labeled options, I'll tell it I want to do a classification tree. You do a classification tree if you had a categorical dependent variable, a regression tree if you had a quantitative dependent variable. Well, there's a bunch of options here that you can select, including whether you want to divide the data into a training set and a validation set, which is one of the options. Well, I'm just going to take all the defaults here. Again, you can look at our longer video on to see a discussion of some of the options. We have various tables and graphs. I'll just press OK. What the program just did is it actually created a script, sent it to R together with the data. R did the analysis and pushed back the output. And you can see up here the actual code that was sent to R. And here, the tree that R fit. Now, quickly looking at the tree, the way you read a tree like this is it says, take a particular observation. If the petal length is less than 2.45, classify it as setosa. If it's greater or equal to 2.45, look at the petal width. If the petal width is less than 1.75, come this way, look at the petal length, then look at the sepal length, and you'll classify it either as versicolor or virginica. If petal width is greater or equal to 1.75, come this way, look at the petal length, and actually regardless of the petal length, it'll be classified as virginica. The reason, incidentally, there are 2 leaves in the tree right here, both ending with the same species, is that there's also a probability distribution at each of those nodes. I can look actually at the node probability table, and down here in the bottom 2 rows, you'll see information on those 2 leaves. If you go to the rightmost leaf at the bottom, there's a probability of 1 that you're virginica. If you go left at that last node, well, it's a 1/6, 5/6 split. So the probability distribution is a little different at these 2 nodes. Anyway, you can see that we've made it very, very easy to interface to the program. You wouldn't even know that R was doing the work underneath, but it is. All right, back to the PowerPoint slide. One last section of Statgraphics that I wanted to make some comments about, and that is changes that we've made to the installation program. Incidentally, I will post these slides here on our webinars page probably before the end of the day, but certainly by tomorrow, so you can read through them at your leisure. There are a couple changes that we have made to the installation program. We've created an online registration program to hopefully make installation simpler. What the online registration program is, it's a website where you register your email and with a username and password, and then attach a particular serial number to your email. it makes it easy for you to go in and see the status of your serial numbers, your site licenses, your trial versions, whatever it might be. It's also set up so that activation no longer requires administrative rights. You still need administrator rights in order to install the program. That's not going to change. That's true of every program. However, activation and deactivation of Statgraphics 18 does not require administrator rights. Now, that brings up the point that we have a new option in Statgraphics that makes it much easier for you to move your license from one computer to another. Within Statgraphics 18, you can deactivate now the installation on a particular computer and then move your license to a different computer. Makes it a lot handier when you're getting a new computer. You can just basically deactivate it on your old machine, activate it on your new machine. Now that's all done automatically, and you can keep track of that through that online registration program. The online registration program is incidentally at the URL register.statgraphics.com. If you want to use Statgraphics, you go to that site, Statgraphics 18. You set up your username and a password. The username is based upon your email address. And then it will show you information about any trial period you have, what serial numbers are registered to your email, how many activations you've had, and if you have a site license, a university site license or something like that, it will let you see the status of that. We've also added to Statgraphics a network management program to make it easier for network administrators to manage their license. It's a separate application that you install on the network manager's client. It lets that manager enter the serial number, choose the directory in which the shared license files will be placed, and activate the program. It also keeps track of the number of seats associated with any particular network serial number and shows at any point in time how many seats are in use or checked out. And I think I did mention at the beginning of the webinar that we do have the ability through this network management program to take, for example, one seat of a 5-user network, check it out, activate that seat on a particular user's laptop so they, for example, can go out into the field with that license. And then when they come back, they can check it back in through this network management program. So that gives network users considerably more flexibility in the use of their license, because I know that there are times when people would like to take one seat of a 5-user network, as I said, and install it for exclusive use for some limited period of time on a particular laptop. Okay, well, that was about all I had a chance to say in an hour. I did not want to go too long. This webinar will be posted at www.statgraphics.com/webinars, as will my slides. Sometime, hopefully by the end of the day, but it might be tomorrow morning. I also mentioned, I think before, that there are over 50 videos, one for each of the new procedures in version 18, and they're available now at www.statgraphics.com/instructional-videos. They go in depth into each of these different additions to version 18 that I can only cover at a fairly superficial level in this particular webinar. Okay, hopefully you found that useful. I'll now see if there were any questions that were submitted. And hopefully I can see the questions. I'm having a little bit of trouble here seeing it on my screen. All right, let's see. Here's a comment from a user in Colombia. Thanks for the presentation. I use Statgraphics with my students because it's easy to use and very complete. That was a comment actually from a user in Colombia. Is that the only question? Grant? Grant? Were there any other questions? I only see one. Just one? Oh, now I see another question. It must have just come in. Equivalence tests. Must the number of observations be equal? No. I do not believe that, because it's doing two one-sided t-tests, and the t-test does not require equal sample sizes, so these tests would also not require equal sample sizes. All right. Another question. ARIMA time series simulations. What are the starting values? This refers to a Monte Carlo procedure in Statgraphics. It's found under Tools, Monte Carlo Simulation, ARIMA time series models. In that particular procedure, what we do is we simulate time series. We generate random time series from a particular autoregressive integrated moving average model. The question is, what are the starting values? I believe, although I'd actually have to double check, that what we do in those simulations is probably start at the mean, run it for some length of time, long enough that those the initial effects have disappeared, and then generate the random samples. I'd have to check the documentation to be sure on that. I don't remember that off the top of my head, but I know we do something to run it long enough so that the initial values don't have any impact. Oh, here's a question. For what additional R procedures are you working on? Well, I don't know how much I want to give away. You will be seeing some of these come fairly shortly. I'll just tell you one. The one that we did, which I think you'll find very useful, which is related to CART, is something called random forests. In a random forest, you generate a whole forest of trees, and you combine the trees together to get a general sort of final consensus model. It's an example of what's called a machine learning process, where you let the machine basically learn what's a good model by generating many, many, many models, a whole forest of trees, you see, and then combining the information from those trees together. Okay, another question. When R updates irregularly, what happens to Statgraphics' previously installed packages with output done in those packages? Typically, when R does updates, and they're constantly doing updates, the packages will either be compatible with the new update or themselves be updated to run with the new version of R. If we see R come out with a major release that breaks our interface to some of those packages, we'll have to go back and fix the interface. I haven't seen that being a problem yet. Of course, R has come out with several minor updates, but not a major update. But we are certainly committed to maintaining the integrity of that interface. Machine learning. What is machine learning? Well, machine learning is basically an algorithmic approach to the development of models. It refers to methods in which you use basically the power of the computer to learn what models are good, what models work on a particular data set. Typically by having a training set and a validation set. And the power of today's computers, lets you run various algorithms and do an awful lot of computation, fit lots and lots and lots of models, and combine the information, potentially from multiple runs together to get a good overall model. Basically, I think of machine learning as an algorithmic approach, or a collection of algorithmic approaches to fitting models that really makes use of the power of the computer to do lots of things very quickly. And finally, someone says, "Hooray, this is the webinar I was hoping for." Well, that's good. I had intended to do this webinar a while ago, but I've been doing a lot of posting on our blog and developed those 50 videos with an in-depth coverage of each of the new additions for version 18. I was glad to finally be able to do a overview so that you could see in the space of an hour all the neat things we've added to version 18. All right, well, that seems to be the last question. I thank you all for your attendance. I'll be trying to get back into doing these webinars, hopefully once a month again for a while, as long as we get as good attendance as we got on this one. So have a good day, and I'll talk to you soon.